programming knowledge to solve those hard ones. All right, so this is not, that's not new. So we've got these two categories. V is a function of x. I've not yet done an example. And A is a function of x. I've not yet done an example. So it's a little early for me to summarize the procedure when we haven't yet worked the problem yet. So, so for this procedure, let's wait and do an example. Then we'll see if we can summarize how we would actually go about this. Okay, suppose we're given our velocity is equal to 2x plus 1. And suppose I wish to find position as a function of time. Where should I start? Roger.
Rewrite v as dx over dt.
Yes. If you said you were stuck, didn't know how to start, and didn't try that. Oh, I wouldn't say that, but I would throw up my arms. I'd say, I give up. I don't know what to do. So what you should try for all of these problems is v is dx dt, a is dv dt. So if you haven't even tried that, and you say you're stuck, then it's difficult. Okay? So please try that first. So Roger's saying, okay, he doesn't want my RAF, so he's suggesting we start by replacing v with dx dt, and then see where that leads. Okay? What should I do next? Anybody?
Separate.
Edgardo?
Separate.
Separate. Okay, so and how would I go about separating this? What should I do to each side?
Multiply each side by dt and divide each side by 2x plus 1.
Good. Okay, so we'll bring the dt over here, 2x plus 1 down over there. So dx, 2x plus 1 equals dt. We will now integrate. But I think this is going to be one of those problems where we're going to need an initial condition. We're doing some kind of integral, so I'm integrating position and time. So let's say as part of our example, we're told that the initial position is equal to 3 meters. Okay, so when time is equal to 0, x is equal to 3. Those have to correspond. So I put a 0 in for my initial time, and a 3 in for the initial position. I integrate from 0 to t and 0 to x. If you're looking at, I can't remember how our textbook does it, but many textbooks don't like the idea that the variable of integration is labeled the same as the limit. So they'll put a prime on all those, so that you can tell that the final position x doesn't mean the same thing as this changing variable inside there. I'm not sure myself which causes more confusion. In fact, I've leaned slightly on using the same name in both cases. Integral from 0 to t dt is a t. This guy over here, you could do a u substitution, make that your u. Many of us have done enough u substitutions. Not all of us. Some of you may need to use a couple more. But if you've done enough u substitutions, you can kind of see in advance how it's going to work out. So when you do the u sub, you're going to get the natural log of 2x plus 1. But you're going to have to multiply by a 1/2 in the front. Because when I take a derivative of the natural log of 2x plus 1, I'll get the extra 2 coming out front, which will cancel that 1/2. If this seems like magic, then do the u substitution. The u substitution will take you an extra minute. However, you'll get it right. So the slowest way to work through dynamics is to get stuff wrong. So take the extra minute, get it right, and then wait until this pattern reveals itself to you personally, and then start using it. I need to put my limits on. I'm going from 3 to x, so I get 1/2 natural log of 2x plus 1 minus 1/2 natural log of 7 equals t, which gives me, now I'm just going to do some algebra to rearrange. I'm going to combine the two natural logs. So we get the natural log of 2x plus 1 divided by 7 equals 2t. So I get e to the 2t equals 2x plus 1 divided by 7, or 2x plus 1 equals 7 e to the 2t. Subtract 1, divide by 2. And I've now got my position as a function of time. It has an exponential term in it. When we get to the end of these kinds of problems, I know I'm watching the clock, I've got 10 minutes. So when I get to the end of these kinds of problems, I want to be able to check my work. If I can't check my work, I have to be perfect, which is usually not human. Most of us make mistakes. I certainly do. So I need to check my work. If I don't check my work, I'm going to be wrong a lot of the time. So several things we can do to check our work. We can check with units. I did some of that before. Maybe more important even than checking with units is to check to see if the answer makes sense. This says 7e to the 2t. So as time gets bigger, this is telling me that the position is getting bigger really, really, really rapidly. So if I plug in a 3 into this equation, 7e to the third, 7e to the 6th, because 2 times 3 seconds would be e to the 6th. E to the 6th is like 300. 7 times 300 is 2100 divided by 2, so it's going to be a big number. But when I plug in 10 seconds, so just a couple seconds later, e to the 20th is a gargantuan number. Okay, so the position is changing very, very rapidly with time, according to my answer. Let's see if that fits the original problem. So let's check this out. Okay, this tells me that my velocity is equal to 2x plus 1, and I start at position 3. So here I am standing at position 3. What's my velocity according to that equation? 7 meters per second, okay? So I'm moving at 7 meters per second this way. Since I'm moving in the positive direction, what happens to my position? Does it go up or go down? Go up. So I'm moving at 7 meters per second. So in 1 second, I've gone 7 meters this way. So I started at position 3. 1 second later, what's my position?
10 meters.
10. What's my speed according to that? 21 meters per second. So I've sped up quite a bit. In the next second, what's my new position? I was at position 10. I'm now going 21 meters per second. So a second later, what's my
31 meters.
31 meters, and now my speed is 63, right? Yes. So this equation describes somebody who's moving this way and speeding up very, very, very rapidly, because the further you go this way, the faster you're going. So you go this way even faster. So therefore you speed up even faster. So the exponential behavior here, e to the 2t, fits this scenario that we have there. So if I'd gotten a minus sign here, I'd know I was wrong, because that wouldn't fit, because e to the negative 2t, instead of getting bigger and bigger and bigger, is tapering off to 0. All right. So I did one check on this where I checked just to see if the shape of that graph made some sense. Let's now do the other part of this problem, which is we're given velocity as a function of x. We found x as a function of t. So I got x as a function of t. How can I get acceleration as a function of t from velocity as a function of x? So if I'm given velocity as a function of x, and instead of being told to find x as a function of t, I need to find the acceleration as a function of t. Can someone give me one approach, even if it seems a little labor-intensive to do that? I've got my hand up. James, you go ahead.
Would you have a equals dv dt? Would you use that, but then take the integral and solve for v and then plug it in? So like the integral of a dt equals 2x plus 1. Or you could do that.
Okay. Well, I'd be stuck right away then, because a derivative of that with respect to time, I don't know. I can take a derivative of that with respect to x. It's got x's in it. If x were a constant, then the derivative would be 0. But is the position a constant for this case?
No.
Do I end up just standing still? No. So this derivative of x with respect to time, I'm going to be a little bit stuck there. Good thought, though. So James went back. At least he used this equation, tried to do something with it. There's an...
Wait, well, that's not what I said.
Oh, sorry.
That's not
What did
close.
you say?
I said if you multiply, if you use a equals dv dt, multiply dt, so it's a dt equals dv. And if you take the integral of that, then it's the integral of a dt equals v. And then plug v in, and then plug 2x plus 1 into that, but
It changes v.
changing v.
Because it would be v final minus v initial. So,
Yeah, I don't know.
well, the problem is I wouldn't be able to do this integral because I don't know what a is yet.
Yeah.
So a is not a constant, so I can't pull it outside. Good thought, though. So what James is doing is exactly what I want all of you to do. Get to a problem like this, brainstorm some ideas. Okay. If you're given v as a function of x, can you get x as a function of time?
Yep.
Okay. We just did that, right?
Take the derivative of x of this equation.
Yeah.
Get velocity and take the derivative of that.
Yep.
Get such.
So what Vaughn's saying is, hey, wait a minute, this is the easiest case ever. That's back to here.
I thought there'd be something different.
Given x is a function of time, I can get acceleration by taking a derivative to get velocity and another derivative to get acceleration. So if you're given v as a function of x and you want a as a function of time, you need to go get x as a function of time even though you weren't asked for it. Okay? Now, sometimes emotionally that can hurt. I know when sometimes I tried out some basic questions of the computer program on my wife. She hates the idea that she has to do something that she doesn't get credit for to then have to do something else to it to finally get the right answer. That just seems wrong to her at some deep level. And I suspect if you're normal, maybe it feels wrong too. So you almost like, you feel okay if it was part A, find x as a function of t, and then part B, find a as a function of t. Then you feel okay, because I got credit for that first part.
I just not waste my time, but
Yeah. So, but that's the easiest approach. Is it possible to do it the other way? James was starting to come up with some other ideas. Is it possible to make those work? Yes. But I think this is the easier approach. Plus, it relies on a skill that you have to have anyway. So I think it's easier to limit the total number of things you'd have to do rather than have another new approach for this one. Okay. The last one I'm actually going to have to mostly put off until Friday. So I'm not going to quite finish this. But let me plant an idea in your head for this last case. I put this one off to the end because it's the hardest. So I'm going to outline two approaches and you can pick which one you like better, but I'm not going to do an example. I'll do an example on Friday with this particular one. I'm given a as a function of x. I'll write that as dv dt. As it stands, there is no way to separate that. The whole principle of separating was I had to have all of one type of variable on one side, all of another type of variable on the other. My equation has two sides. Here I have three variables, x, v, and t. I've only got two sides of the equation. Separating them is impossible. However, I can use a trick. None of the rest of that is what I'd call a trick. It was just reusing this and that calculus. I'm now going to do something that's a trick, meaning something that's a little clever that any of us might not have been expected to think of on our own. So let me show you what the trick is. I'm going to replace dv dt with dv dx times dx dt. That's a legitimate thing to do. Notice how if I wanted to go back the other way, I can cancel the dx's and get back to dv dt. What's another name for dx dt?
Velocity.
Yep. Now, how many different variables do I have? Two. So now that I'm down to two variables, maybe I can separate. In fact, to separate this, what should I do?
Multiply by dx.
Multiply by dx. I get a is a function of x, dx equals v dv. I've got all the x's on the left side, all the v's on the other. And when I integrate, this is going to end up giving me some velocity as a function of x, which takes me back to this. Remove the weight because we already did an example with that, and I'm off and running. So the trick, and it's actually a trick that's not unique to this case. It's a trick that we're going to use multiple times this semester. As an engineer, you'll use it in multiple classes. The idea is, if you don't like this derivative as it stands, if I don't like it being written as dv dt, maybe I can change it to a different form that is more useful for me to work with. In this case, I rewrote dv dt as dv dx times dx dt, which dx dt was a v, so it's dv dx times v. And it's time for the quiz. So if someone had a question, let me try to take that.